Hello, so it's my pleasure to introduce the third speaker of today's seminar, which is Daniel Fuster. Daniel is a chemical engineer from the University of Zaragoza. He then did the PhD there on the dynamics of cavitation, right? And then he moved very briefly to Paris, to the same place, to the CNRS and UPMC, very briefly, right? Like a few months, something like that. Then you moved to Caltech.
1 year and a half.
Oh, 1 year and a half. Okay, so 1 year and a half. Then he moved to Caltech when he was doing the postdoc for another 2 years, I guess, right? And then he went back permanently to the Université Pierre and Marie Curie and the CNRS, where he's staying right now. And he's going to talk about atomization regimes in planar co-flowing fluid sheets using Gerris. So it's a rather technical and interesting topic.
Okay.
So Daniel, thank you very much.
Thank you. Thank you very much for the invitation and organizing this nice seminar. I think it's a great opportunity to interact with some Spanish colleagues, and it's not always easy to find in conference and so on because you are in different sessions. And I think I'm going to switch it off because otherwise they are coupled.
Maybe they are coupling, right?
Hola? Ahora? Yes? Okay. So I'm going to talk about primary atomization regimes in two planar co-flowing fluid sheets using Gerris. So it's going to happen again every time I approach this. I don't know.
You can take away the portable microphone because with the other it was working okay. So
Yeah, this is what I'm, okay. It's fine? Well, I'm going to start anyway. So the outline of this presentation will be a first introduction about the motivation of this work, and then I will briefly explain the theoretical approach that we typically use to study these kind of problems. I will present the code. That this is one of the main reasons why I would like to talk about this specific problem. So I basically work on cavitation, and this is the topic I like the most. But, well, then I moved to Paris, and then all the people there use Gerris, and they made me use Gerris. They obliged me to use Gerris. But then more and more people is using it, and I think, well, some of my experience might be of interest for you, maybe more than the experience I have in cavitation, where people really don't care about what they do. So just to show what the code can do, and it's a little of publishing the code, but, well, yeah, this is what it is, science sometimes. And then the experimental validation that we did for the particular problem we were interested in. And, well, finally, what interests us is the investigation of the mechanism that leads to the breakup of a liquid sheet. So the experimental setup that we are interested in this talk is something like that, where we are injecting water in the down sheet, and then we put gas at some high velocity. I guess everybody knows there is a splitter plate in the middle with a given separator plate thickness and an angle. And then what we are going to, well, we can distinguish already two regimes. The primary atomization regime is the regime in which we have the appearance of instabilities. Typically, they are Kelvin-Helmholtz-like instabilities, where because of the velocity difference between the two phases, we have some small perturbations that grow in space and time, and finally they give to the appearance of ligaments that go into droplets. And then we have the second atomization regime, which is pretty more complicated, and where we are not still quite there, but yeah, this is something we can do. So this is an example of the kind of images we get from experiments. The experiments are done in Grenoble. So here we have a liquid sheet with a relatively low velocity. Here we are putting the gas at high velocities. And here we have the interface position as a function of space. It's a given snapshot. So here you cannot really see it, but we have the splitter plate. And here we have the initial appearance of instabilities. So here we can draw the line roughly about the shape of the instability, and we can see how a wave appears, and here how the wave breaks into droplets. So in principle, this frequency is going to give you the rate of producing droplets in a given application. And then what we are interested is in measuring the frequencies or the wavelengths that are appearing in this process. So if we look from outside, we have pictures like that where we can easily characterize the wavelengths we have. So the main point of my postdoc and, well, some of the work that I've been doing since I'm a permanent researcher is trying to compare or to know where we are regarding the comparison between experiment, theoretical work, and simulations. So obviously, it's not me who do all the job. There are a lot of people involved in that, and we are trying to clarify the comparisons. So just a rough review about some things we were looking at. First thing we have is a dark liquid, a potential cone, that is the region where the liquid is not really influenced by the presence of the instabilities. So this is a potential cone that has been experimentally characterized as a function of the momentum ratio and the height of the liquid. And here we have some comparison with the numerical results where we have the position of the interface at every time, and we see how this red line is the theoretical prediction, well, the experimental correlation, and we see how the numerical result correctly reproduce this potential cone we have in this primary atomization region. Then we can do more fancy examples where we have a swirling jet which is atomized into droplets, and we measure at the droplet distribution. So this is the experimentally PDF that we have, and here we have simulations. Well, we have relatively good fitting over there, and then at some point we cannot really resolve very, very small length scales, and we have to stop, but well, we have something that look like the experimental PDF. But as I was seeing, the specific topic I'm going to tell you about today is the appearance of waves near the splitter plate. So just to show you, I'm going to see if a typical example of the kind of simulations we are doing. We have this video where we can see here the position of the interface as a function of time. Here we have the splitter plate, and we have the appearance of strong waves appearing with a given frequency. Here we have one wave. Now we will have another one. Here in colors we see the norm of the velocity. Just to give you an idea of the intensities, well, here you have obviously much higher velocities than in the liquid. And then what we want to characterize is the kind of flows that we have in the region. So to do this, we are going to use Gerris. That is a code that allows us to perform adaptive mesh refinement. And the adaptive mesh refinement, basically what it allows us is to concentrate the grid in the region that is where almost all the physics happens. So, well, there are situations where the boundary conditions really influence the frequencies that you are measuring here. So when you are doing numerical computations, you really want to get a very big domain where you can get rid of the effects of the boundary condition that might give you some mismatching between numerical predictions and experiment. And here we see, this is dots, this is the grid points. We see how we can very fine the interface. We can refine a lot the region where we are interested in the physics, and then we can course the grid far away from the region that it interests us, and to perform simulations which are relatively expensive in a much efficient way. So when we are doing experiments, well, we are almost always doing the same. We get the position of the interface by a laser, and we get the profile of the interface as a function of time. And then what we can do is to do the Fourier spectra, that this is what we see here, as a function of the downstream distance. And then what we see is a clear peak that appears for a certain given conditions, and this peak is relatively independent on the downstream distance up to a given distance, obviously. So there is this clear peak that appears in the spectrum, and we want to understand how it behaves, and it's relatively independent on the downstream distance. So here the point is that while people develop linear theory typically to try to understand what happens, and people were relatively happy because with just temporal linear theory implicit, they were getting the right scaling where they were looking at the wavelengths or the frequencies are equivalent. As a function of the gas velocity, they were getting 1/2. But indeed, when you were looking at the exact values, they were over predicting the experimental values. So here in red, we have the experimental values. We had the predictions of the linear theory in a temporal framework. And then Stefan was working with a German student in the viscous temporal linear theory. And then what they found is that something that doesn't fit the experiments, but it's not only that, it doesn't even fit the scaling. So people were a little bit saying like, okay, you are complicating the linear analysis, and then you get something that is even worse. So it's not really the thing that you should do. And Stefan was not so happy because, well, real world is viscous. So if you put viscous in a theory, it should improve the predictions. And if it makes things worse, it means that you are really missing something in the theoretical approach. So here the idea was first to try to see how theory compares to simulations in a framework where we hope both situations, I mean, theory applies. So obviously, if you are exactly in the framework of the theory, then simulations should reproduce the results of the theory. Then we can go to the exact conditions of experiments and to see how the numerical two compare to experiments. And by doing these two comparisons, we can try to understand why theory doesn't fit experiments for at least this given configuration. So, well, they are air-water simulations for very big domains and with very different length scales, so it's required to solve different numerical issues. And, well, this is the main thing we basically do at D'Alembert. So, yes, I'm going to introduce very briefly the theory that we typically use. I was talking about the temporal analysis. So basically in the temporal analysis, what happens is that, well, we fit we are in a box which moves at a given velocity that already we don't know. We have to determine, which is something which is not always good in a theory. You have to say what is the velocity of the moving frame. And then we are going to fix the wavelength, and we are going to see one perturbation of this wavelength, how it grows in time. So the window is going to move. So basically the formulation, well, you use string lines where you impose a perturbation with a given wave number, which is real, and then the frequency is complex. We have a real part and a complex part, and the complex part, what is telling you, is the growth of the instability. So we can solve these equations in VC without taking into account viscous terms, or we can include viscous terms, in which case we have to solve for the Orr-Sommerfeld equations. And we have to put something as an input. We have to determine the base flow that we have, and we have to, every time we have to put a wavelength, and then for this wavelength we will work out the growth rate. So as an output we will get the growth rate and the frequency. So, well, one important thing already was what about the base flow? So typically in the theories people were using base flows like this one, which is implicit, which is just a linear profile where we have a boundary layer in the liquid, we have a boundary layer in the gas. If we include viscous effects, then we have to introduce error functions to reproduce the kind of profiles that you have. But in fact, there is something which is already remarkable, is that in a real configuration we have a splitter plane, we have non-zero boundary conditions at the surface. So in fact, there is a velocity defect here, which is going to modify the velocity profile, and it will take some distance to this profile to develop and to come back to the traditional base flow velocity profiles that were typically used in theoretical approaches to try to predict the frequencies. So, well, here we can generalize the kind of flow we put by introducing a velocity defect parameter. So if we put it to 1, we get the traditional velocity profile like here. And then if we put it to 0.1, we get the velocity profile with a defect. And then we can compare the theoretical predictions and to see how they compare with the simulations. So well, this is just a theoretical scenario where basically what we did is to reproduce these conditions in this guy here with viscous effects. viscous because, well, when you put viscosity, the theory is even worse. So we wanted to know if we try to simulate this process, we are still getting the right solution from theory. And we see here how the theory and the simulation results fit well for the different wavelengths. So here, every point is a simulation. We fit the wavelength, we measure the growth rate, and we see how the theory and the simulations work well. But as I saying, okay, this is a theoretical case. It's working well with the simulations, but what happens is that with experiments, it doesn't work so well. So in fact, well, one of the solutions is to say, okay, in fact, the theoretical analysis, the temporal analysis, might not give all the information we have. Maybe the spatio-temporal analysis gives you some more information about how the system behaves. In this case, what we have is a string line with exactly the same kind of behavior, sinusoidal variations. But in this case, it's not only the frequency, which is complex, but we introduce also a wavelength, which is a complex number. And then, well, we still have to solve for the equations. So we have modified our Sommerfeld equations. And we need also, as in the temporal case, to impose some base flow profile and input some real wavelength and complex frequency to work out the real part of the frequency and the spatial growth rate. So the main difference between the temporal and spatiotemporal analysis is that the spatiotemporal analysis allows us to distinguish between the convective and absolute instability. So basically, a convective instability is that we put some noise at a given location, and this instability is going to grow, but it's going to be affected with the flow velocity, and it's going to it's going to be affected. It's going to disappear after some time. The absolute instability, what happens is that this small instability that we put in the flow propagates not only downstream but also upstream, and then typically what happens is that this is the convective case where we have different growth rates as a function of the wave number. This is very clear. You see plots which are continuous. When we start getting a global mode, we start to get diagrams like that, where typically we identify a saddle point, which is the most unstable frequency of the system. So, well, we will come back a little bit later into this, but what is important to keep in mind is that, well, we get this kind of fancy diagrams where we can get a saddle point where it doesn't tell us that every stability grows with a given growth rate, but it gives you information about the only frequency that we are going to observe in the system. So, okay, we have explained more or less what we expect to see from the theoretical point of view. Now what we are going to perform are some simulations. So as I'm saying, we will be using Gerris, which is a free software that everybody can download and use, that tries to solve for the differential equations describing the fluid flow. That is the Navier-Stokes equation. It has some appealing characteristics that makes adaptive mesh refinement in second order in space and time. You can parallelize it quite easily, and it has mainly very accurate schemes. That this is the main characteristic with respect to other fluid solvers. They have really worked a lot on the both advection scheme and the calculation of the surface tension. So here there are just some examples. Here Popinede, he was trying to simulate the break of a wave where we have very small length scales that we want to capture thanks to active mesh refinement. We have atomization simulations. We have the jet that breaks into droplet. We have cavitation, and we have other applications where we want to use these features. So here we see the characteristics of the grid, where we are able to really refine a lot in the ligaments, and then we course the grid in these regions where the curvature is not that high, and we don't need so much precision. Oh, so well, one of the things I wanted to mention is that one of the typical annoying things that it occurs is the appearance of very small droplets that you have to deal with. So already you have a small droplets. Even if we do adaptive mesh refinement, we have here a box of around 4,000 cells just to capture a small cell that we are not resolving well anyway. So we are using a Lagrangian particle method and then a conversion just to keep the physics write and saving a lot of computational time. So basically what we do is to transform the particles, to treat the small droplets into particles. I don't know if you are able to see that. And then whenever it approaches a well-resolved interface, we transform it back into particle, into a well-refined droplet, and we are going to see here the splashing in a lake. So the particles splash into the surface, so we are still getting the turbulence which is generated in the surface. Here we can measure the PDF, and we don't need really to refine in these regions where it will be really expensive to deal with all the simulations. So well, for the particular problem that interests us, we use these parameters. So it's an air-water simulation with, well, some non-dimensional numbers that are here. The most important, or one of the most important non-dimensional numbers is the ratio between the dynamic pressures, that is the density times the velocity squared. So the higher it is, the more stronger the atomization is typically. And then, well, we did some simulations in 3D. I'm going to skip it. They are not very long because they are expensive, but what we check is that appearance of instability, which is consistent with what we see in experiments, is mainly a 2D effect. So we can use computational domains like the one you see here, where we are going to try to see if the code is able to predict the frequencies we see in experiments. So even these conditions are not very easy to get, but here we get the experiment frequency. This is the Fourier spectra. Here is the experiment frequency, here is the FFT, here we get the peak. The problem is that, as I will see now, the simulations cannot run very long, so the FFT is quite noisy, but already you can see a frequency, a peak frequency that is already on the range of the experimental frequency. And then what is interesting here is to see how the spatial linear theory already captures really well, at least for this number, the frequency we were observing. So this is the first finding we did, is that in fact the spatial linear theory works quite well compared to the temporal one, which is here, in order to predict the frequencies in some conditions that we will get a little more in detail now. So the problem here, already you can see it, is very hard to understand to get a clear predict from simulations, because we need a very large computational domain, and the conditions, well, there are plenty of numerical issues that most of you, if you do numerical computations, can imagine. And, well, yeah, we need a relatively large computational domain, and the density ratios are so large that it slows down a lot the convergence of the Poisson solver. So the conclusion of this is that, okay, we are fine. We have a code that more or less compares with experiments, but we cannot really exploit all the parameter range with this, because simulations take so long that it's impossible to understand anything else except than saying that, okay, we are able to reproduce the point that we were interested in. So the point is the spatiotemporal theory always working? Or what is the influence of different parameters, or this initial issue we were having about the temporal linear theory, the scaling, and everything, how all this works. So to make this, what we are going to consider is smaller computational domains, and where we can perform long simulations, exhaustive parametric analysis, and accurate frequency calculations, and to compare theory and simulations. Here, obviously, we cannot do experiments, because we are going to decrease the density ratio, so that the convergence of the Poisson solver is much better, and we can go much longer. So here the Fourier spectra is already very neat. So the peak you get is clear, and there is no doubt about the frequency we are measuring. If you look at the kind of simulations it gives, you will see that, well, at some distance here, we have the appearance of waves which are very irregular frequency. And obviously, once you do the FFT of the position at a given position, you get a very nice peak. So I get around 100 waves, and then I do the... So Then running the theoretical code, what was interesting to see is that in fact there is you can distinguish the transition from convective to absolute stability as a function of the momentum ratio if you fix all the parameters and you only change the liquid velocity. So this was something that people were not really looking into this. The people that do theoretical analysis, they try to give you all the parameter range, and sometimes it's very hard to extract the useful information out of that, even when it's there. I'm not saying the information is not there, but if nobody explains you, it's very hard to see. So here, basically, what we do is just to change the liquid velocity, and by changing the liquid velocity, we see how we change from a convective instability from a global instability. This is theoretically. So basically, as I was saying, what happens is that we expect a large momentum ratio to see only one frequency in the system, whereas at low momentum ratio, the idea is that we are going to have some input noise, and this is going to be amplified according to the growth rate that can be at, which is function of the frequency, basically. So to see this, what we do is to perturb the flux with some frequencies, some forcing frequencies. Then what we expect to see is if it's convective, these forcing frequencies are going to be seen with some amplitude that depends on the growth rate. If it's global, these forcing frequencies are not going to be seen because they are going to be completely killed by the global mode that is moving up and down on the domain. So if we go to the low momentum ratio regime, where we expect the stability to be convective, we see here the growth rate, well, the Fourier spectra as a function of the forcing frequencies. So here are all the forcing frequencies we have. And we have, as well, we see already the amplitude obviously is the same for all the frequencies. And we see how the amplitude of these peaks depends on the frequency, so finally on the wavelength. And if we compare with the theoretical predictions, with and without velocity defect, we see how the theory makes a very good job. Here we are really accounting for the viscous effects. If we go to so now we are going to slow down the liquid, and we are going to enter in an absolute regime where we have diagrams like this, and where we can extract the most unstable frequency and mode that we have in the system. So in this case, we have a clear peak. We don't see the forcing frequencies anymore. We only have a clear peak in the simulations that corresponds relatively well to the theoretical predictions. Always, if we put the effect of the splitter plate in the base flow profile, we get a slightly improvement with compared to simulation. So it was a nice thing. Another nice thing is that, in fact, if you do the scaling with the gas velocity, you recover a given slope. That indeed, so here we have the dependence with the gas velocity from theoretical predictions, from simulations, and the experimental fitting that they get. So they get the slopes of 1/2 with respect to the frequency. So we get this nice, this slope that we were measuring experimentally. So here this is the experimental measurement. So we get exactly the same scaling, which is something curious, is that if you do the scaling in the temporal framework with viscous effect, then you get a scaling that is not good. But then if you do it spatio-temporal, then you come back to the scaling that you will have in inviscid, but it's just a casualty. I mean, there is nothing that tells you that the scaling that you get in inviscid flow in the temporal framework is the same that you get in the viscous spatio-temporal. I mean, it was just a casualty, and people were happy just because yes, in my opinion, because they were very lucky. Then what we do, as we were saying, we were just looking at the points at the screen. So we were looking points at the very low momentum ratios and very large momentum ratios. So now what we are going to do is to characterize the kind of spectra that we get as a function of the momentum ratio. So here we have the spectra very large momentum ratio, and as we decrease it, so we are slowing down the liquid velocity, we get something which is more and more noisy, and finally we see all the forcing frequencies here, and finally random noise all about. So here we have this momentum ratio, and what is interesting, and here is the most unstable frequency, how it behaves with the momentum ratio. So what is interesting here is to see that from simulation results you get this asymptotic regime, where indeed the most unstable frequency is completely independent from the liquid velocity. So you can change the momentum ratio, and this most unstable frequency doesn't change. And in fact, in this regime, the spatio-temporal linear theory accounting for viscous effect and accounting for the velocity profile in the base profile, it makes a really good job predicting this asymptotic regime. Then if we go to the temporal linear theory, we get errors of about 20%. So I'm going to run because...
No, eso corres.
No, porque eso funciona.
Yeah.
So this is one thing we already see here. So the linear theory is working quite well in this asymptotic regime. Then if we decrease the momentum ratio, there is a regime where we cannot really talk about a single frequency. And then what I do is to plot here the transition from convective to absolute. So this black point is the last point in a simulation where I get absolute instability. This in line, you get the critical momentum ratio predicted from theory. So it's quite well also. I mean, I'm seeing transition at around 6. Here the theory predicts transition at around 8 if you account for the velocity defect in the base profile. If you neglect it, you get around 1. Obviously, in the linear theory framework, you cannot really predict this transition from global to absolute. So, okay, obviously, remember that I was doing this kind of computations in the low density ratio regime. So the point is that we can see the same kind of transition in the water experiments. So we talk to the experimental people, and then they repeat exactly the same experiments, but in air water conditions. So now they are experiments. I'm not involved on that. And well, I just reproduce the theoretical results, and we get a very similar behavior. So here we get a very clear peak in the spectrum. This is, as I remember you, this is experimental. And then as we decrease the momentum ratio near the critical momentum ratio predicted by theory, we get something really noisy. And then if we go below this critical momentum ratio, so we go from 0.75 to 0.5, we get something which is completely random, and we just see black noise coming from the turbulence on the system. And then if we compare the frequencies, we see here that in this asymptotic regime that we also see in experiments, the spatio linear theory accounting from viscous effect and the effect of the separator plate predicts quite well the frequencies in the region. As we approach to this transition where the stability starts to be convective, then the fitting is worse and worse, and this is normal because we feel that the noise that you have in the system might influence the kind of frequencies that you observe, and then you start to see very, very strange things. And it's also interesting that the transition that you see from this spectrum to this other one, so the transition from convective to absolute, is very, very well predicted by the theory as well, and especially if you account for the effect of the separator plate. So if you don't do that, you can get errors here that are quite large, are of the order of 20 times the momentum ratio that you get. So there are situations, especially for air water, which is really important, the effect of this velocity defect, if you are interested just in knowing if you are in the absolute or in the convective regime. So, in fact, this critical momentum ratio is interesting because finally you might be interested in being in this regime where only one frequency appears and that is it's relatively independent of the liquid velocity. So, in fact, it evolves with the square root of the density ratio, and physically you can explain that by just considering that in fact there is a critical liquid velocity, so that if we are below this critical velocity, in fact the liquid which is swept by the instability, in fact it makes the information be propagated upstream. So this is what makes finally the mechanism to be absolute, because it's not only that the information is propagating downstream, the information is propagating also upstream. And obviously the velocity of the liquid is large enough. In fact, what happens is that we are advecting everything downstream and nothing comes back. So if we switch off the instability or whatever, the system will come back to the equilibrium state. So now, if we assume that this critical velocity scales with the growth rate, we know that this is going to scale like the gas velocity times the square root of the density ratio. So finally, we find that the momentum ratio is expected. We just replace here the liquid velocity by this relation, and we see that this is what we see in experiments and in simulations, that this critical momentum ratio is expected to evolve at the square root of the density ratio, which is interesting for people that do atomization in rocket engines and systems like that, where the density ratio is not always 1,000. And just to finish, one interesting thing here was the role of the separator plate. So in fact, there is two roles of the separator plate. One is the velocity defect that includes, because the wall is non-slip, so basically, even if you have a thickness 0, you will have the velocity defect appearing. And another is really the effect of the thickness of the separator plate on the observed frequencies. So basically what they see in the experiments is that there is a sudden jump from the frequencies you get when the separator plate tends to 0. So it's much smaller than the gas boundary layer. And whenever you start to make it bigger, in fact, this frequency jumps, and we decrease it by factor 2. We can decrease it by factor 2. So in fact, we do some numerical experiments to see if we were able to reproduce this effect, and we see this peak, and we are increasing just the thickness of the separator plate, and we see a similar transition from absolute to convective, where the spectrum becomes more noisy, and finally we get a sudden shift of this frequency by factor 2. In fact, here what we see is both peaks coexist, and then if you make the separator plate thicker and thicker, then this other peak becomes more and more important, and this is the only one you see. So we talked to the experimental people to see if they could reproduce this kind of behavior, and they did experiments with very thin separator plate, with a very thick separator plate, and they measured the spectrum, and well, they still find another time that the frequency is shifted by factor 2, and the spectrum becomes much noisier and wider, because it seems like there are some, something like behaves more like it's a combination between an absolute mode and a convective mode that we don't really quite understand well theoretically. But it's nice that at least the simulation seems to capture well the behavior which is explained experimentally. So finally, what we propose here is a cartogram where we can distinguish different atomization regimes. So regimes where we see clear peaks. Then if we make a thicker separator plate, we can shift this frequency and to put it to a half. And then if we decrease the momentum ratio, so the frequency doesn't depend on the liquid velocity, and then if we decrease the momentum ratio, we have a situation where we basically see the noise and the frequencies which are excited. So that was all I wanted to tell you today. Thank you.
Okay, so it's time for questions. Any question for Daniel?
This flow actually evolves in the x direction, right? So actually you have like different velocity profiles at different axial positions.
Yeah.
It's like, where do you only look at one position, like right behind the splitter plate, or do you take into account like the evolution of these profiles to calculate the spatial temporary stability properties?
Well, yeah, for the theoretical approach, we just take an average velocity profile. So it's a velocity profile that remains constant in space. So
I see this, yeah, because there's this like the relationship between like the local stability properties and the global behavior of the jet. There are some classical papers by Chomas and etc. that indicate that there's actually a relation between the evolution of the growth rate, how this thing evolves with X, and the triggering of the global instability. So you might, try to do that. It's very computational. Like it's a bit of a mess. No, you need to like calculate the stability properties at every actual position and look how they evolve. It's a little bit more involved, but it might be interesting to take a look at that.
Yeah, the main point we were trying to make here, the main point people is interested mainly in industry is what is the simplest model that works.
Yeah, of course.
So obviously once you get to a given accuracy, you can say, okay, I can even do it better. But I really want to know if, for example, the temporal theory works, because the temporal theory is much faster than the spatio-temporal theory. So if it works, I want to know where it works or it gives me the right answer. And this is, for example, why at the beginning they were so happy with the temporal theory just giving the right scaling, because then you put a factor that you don't know from where it comes from, and then you put it in your model, and you have a very simple model that gives you the right answer. So here we try to go a little more deep into that, more than trying to really validate or to see how well we can do. And in fact, well, I'm not in charge of developing the theoretical code. So yeah, I agree that you can do more fancy things like this that really improves a little bit the prediction. But what is remarkable is that at least for the conditions we have here, we saw the fitting is I would say better than everybody could have expected. Because even you could say, okay, there are nonlinear regimes that are going to shift also the frequencies. Because when I saw the video, the frequencies in the global mode regime become so large from the beginning, from the splitter plate, that you even think that linear theory is right. Yeah. So it was, I mean, maybe it's a casualty also, because, you have quite a lot of points that really fit with the experiment and so on. But yeah, I mean, there is a point where you have to say, okay, I'm going to stop developing codes and to make it more complex because it really doesn't make sense.
Then just one brief question from the practical point of view. When doing the numerical calculation, you say you need a very big domain. Like how big? Like how many diameters or how many distances do you have to take into account, downstream? Yeah,
so that was curious. I don't really, because there are people who do sensibility analysis about how the global mode or the unstable mode is sensible according to. So there are regions of instability, of sensitivity. And I haven't done this kind of analysis, but what I can say from my experience is that inner water simulation is really big. So I had to take something like 100, or it was enormous. If you really want to get rid of all the effects of the downstream of the boundaries on the frequencies that you have in the splitter plate, but at a small density ratios, I could do very, very small boxes, and the results are still consistent with the theory. So I guess, I mean, more clever people than me can do sensitivity analysis and to see how the mode is influenced by the noise that you have downstream and things like that. But I haven't. I don't have.
So I guess Álvaro has a question.
So yeah, my question is on droplets. Surprise, big droplets. So you mentioned that, I mean, it's very costly computationally to solve all the grids and all the details for that. So, but still, then I'm not sure. First question is, I'm not sure I understood what you do exactly. So you kind of fit with the Lagrangian approach?
Well, yeah, basically you have a continuous interface, and whenever a small droplet is there, you detect it. Yeah. So it's a technical thing. And then you remove it completely and you put a Lagrangian particle. And then the point is that you still want to capture the effect that this particle is going to have back in the liquid. So whenever this particle approaches to a continuous interface again, you transform it back to a droplet and you see how it splashes in the... So it's very, it has some cost. It's not free. But it's still better than tracking the particle everywhere, every point, and things like that.
Well, you still have to do it, no? I mean, you still have to track this
particle. But it's one point.
It's 1 point,
And well, I show you, even if you want to resolve a droplet badly, you will need around 4,000 grid points. So you transform 1,000 in one, so you get really a big.
And then the second question, still, I mean, you could then, in theory, I mean, theoretically, you could actually measure the droplet distribution, no? In these cases, and so you have results on that, or?
Well, yeah, but this is a bit very tricky. This is what I saw here.
Yeah, because I saw a Gaussian profile there.
Yeah.
I'm not sure if it was.
Yes. It was the comparison for some. Yeah, this one. So this is the simulation PDF. And this is the
Gaussian,
this is the experimental.
That is experimental.
That is experimental. But I have to say that we don't really you don't really see how this start decreasing. So it's like okay. It looks okay, but
you have expected like a bigger tail, no? But I don't know.
Yeah, but what I'm saying is that I'm cutting the grid size here, so I'm kind of cheating. If I have to be honest, because then if you refine more and more, I mean, if you want to really prove that this works, you should refine and capture how it starts decreasing, because otherwise I can have a PDF that grows and grows as it gets smaller and smaller. And well, the point is that here, okay, you transform it back to put it a particle, but when you do this, you have to make sure that you have captured right the process of pinching off. And
that is too much detail for
it can be too much detail. So in principle, we are trying to work in models that detects not the droplet when it's formed, but it detects the ligament, and then you try to predict how many droplets are going to be generated from this ligament. But even these kinds are kind of engineering things where I mean, it's not simple, because in real conditions you have something completely deformated. In a lot of situations, it really depends on the initial condition. Obviously, then you can do theoretical situations where you see the most unstable wavelength and how many droplets.
I thought this was more or less classical from the stuff from Emmanuel Villemot, that he studied all these distributions, and I thought this was well understood already. For what you tell me, it seems that it's not.
No. Well, one thing, I know. Well, one thing is to understand how, for example, the PDF is generated, and this is why we are not really looking at this from simulation. Another is to reproduce it from simulation numerical results. Okay, so to reproduce the PDFs that are well understood from a physical point of view numerically is not something that is done already. And then there are obviously very complex flows where even theoretical analysis doesn't apply, and this is why industrial people want to develop numerical tools that allow you to predict PDF. And Javier also tried to measure PDF, so I guess, so there are, at least from the industrial point of view, there are still a lot of interest in knowing how the PDF. But maybe from the, conceptually they are better understood. It's not something I've been working on.
But I mean, you have enough tools to study that if you have the time and the money.
But normally the tools then you have different regions. So for example, you have tools that tells you, okay, if you have a turbulence level and in the secondary atomization and you wait long enough, what is the PDF which is going to be generated? But for example, in combustion, this doesn't really interest you, the PDF that you have at the beginning, but the time of the droplets that you have at the very beginning, because it's there where the combustion occurs, and this PDF can evolve. So for example, for the frozen PDF, I don't know, maybe I know here there are people that know much more than me, but I think it's a problem that, to really capture all what happens from the very beginning to the very end is not something that theoretically you can say, okay, it's well understood, because it's so complicated and you can have so many different scenarios that finally people really want to do some numerical computations to see what's going on there.
More questions? Yeah. Thank you, Guillem.
Can you put please back the video in which you showed the solution of your simulation? You showed the video in pretty colors about, and you showed the simulation running.
Well, this is a simulation. You mean this?
Yeah, probably. It looked like that. Because it was, I mean, you could see some kind of a pattern that seemed to be domain decomposition. Was that?
Yeah, yes. Then you mean about the grid size?
Yeah, I mean, you had the simulation running, and then you could see kind of a grid that looked like domain decomposition.
Yeah.
Is Gerris doing? Is that domain decomposition done by Gerris?
Yeah.
By the flow solver?
Yeah, yeah.
Because it didn't look so optimal to me. If you look at the load balancing, maybe you could try a different one.
Completely. This simulation indeed I did when I was postdoc.
Mm-hmm.
Well, after 1 year, I was not very good using the code and so on. Now, precisely, I'm working in techniques to try to develop more intelligent adaptive refinement techniques and so on. So, yeah, well, it's always the same thing. Numerical codes, at the beginning, they do what you want, and then you are happy. But then if you want to do it efficient, you really have to spend a lot of time and to understand how the adaptive refinement techniques work, and then you start to see, okay, I could do this and I could work better and things like that. But well, they are so technical things that I don't really explain them here. But I recognize that this simulation was done at the very beginning of my postdoc, where I was so happy just to get a result that I didn't really spend time optimizing the grid and things like that.
It's not more the grid, but if your code is parallel, just changing how your domain is splitted, maybe you get a speed of 2, just because you kind of load balance.
Yeah. We know that. Yes, I know that. I've been doing simulations for quite a long time, much longer than when I did. And I mean, yeah, you're right.
Any more questions? Okay, so let's thank Daniel again for his talk. So I guess we have to again to switch at least file, if not computers.